In this project, you'll turn a Raspberry Pi into a smart photo booth. A camera captures the moment, a button or sensor triggers the shot, and Python saves each image with clean, time-stamped file names. You've already built the foundation for smart robotics. With ESP32, you connected sensors, outputs, motors, Bluetooth, Wi-Fi, dashboards, and alerts. With Arduino, you practiced reliable control through games and robot challenges. Then you compared boards and saw why Raspberry Pi is better suited for images and AI. Now that brain gets eyes through a camera. The goal is to build a small photo booth that behaves like a real system. A person starts it with a button or sensor. The Raspberry Pi receives that signal, runs a countdown, controls the camera, and decides when to take the picture. After the click, the image is saved as part of a photo collection. This is also our first step toward computer vision, because before a computer can recognize anything, it needs images to work with. Later, we can add lights, sounds, and smarter sensors. A photo booth is a small input processing output system. The Raspberry Pi is the brain. It runs your Python program, controls the camera, and saves each image. The camera is the eye, capturing the actual photo with either a Pi camera module or a USB webcam. A trigger input tells the program when to start, using a button, motion sensor, or distance sensor. Feedback output keeps the user informed with a countdown, light, sound, or screen message. Together, these parts turn code into an interactive booth. Camera choice starts with the project's physical needs. The Raspberry Pi camera module connects through the CSI port with a ribbon cable, so it is small, neat, and useful for robots or compact builds. A USB webcam plugs into a USB port, which usually makes setup easier and more flexible. It works well for quick testing, demos, or projects where the camera sits farther away. Choose the camera module for compact integration and USB for convenience. Before touching any camera connection, shut the Raspberry Pi down and remove power. This helps prevent shorts and protects the CSI connector. For a ribbon camera, gently lift the connector latch, align the cable in the correct direction, slide it straight in, and lock the latch without forcing it. The ribbon should sit flat, not twisted or sharply bent. If you are using a USB webcam, plug it into a USB port before boot, then confirm the Pi detects it. Treat every cable as fragile. Before writing project code, prove one simple thing. The Pi can see the camera and save an image. Open a terminal and run a capture command, such as libcamerastillotest, JPEG. If it succeeds, open test.jpg and inspect it. Is the subject facing the right direction? Is the image sharp enough? Is the lighting usable? This quick test separates hardware problems from software problems. If something fails, fix the cable, enable camera support, or adjust the setup now before debugging a larger program. At this point, the camera becomes part of a program, not just a device you test by hand. Python can import a camera library, start the camera, and wait for something to happen, like a button press or motion sensor signal. When that trigger arrives, the program captures an image and saves it with a file name. This is the key step toward a smart photo booth. Inputs, timing, camera control, and storage working together as one automated system. Each photo is saved as an image file, usually in a format like JPG or PNG. JPG is common because it keeps file sizes smaller, which is useful when storing or sharing many photos. PNG can preserve more detail, but often takes more space. Resolution is the other key idea. More pixels usually mean a clearer image, but also a larger file. For AI, quality matters. A focused, well-lit, well-positioned image at a high enough resolution gives the system better data to view, sort, and analyze. If a camera saves every picture as something like IMG_001, a later session can reuse that name and overwrite an older photo. A safer habit is to build the file name from the moment the picture was taken, plus a short description. For example, 2022-06-15-15-24_birthdayparty.jpg is unique and meaningful. The timestamp separates one image from another, and the description reminds you what it contains. Storing related photos in folders, like events, vacations, or family, also helps. That same organization becomes valuable later when computer vision projects need clean, traceable image data. To make the booth feel interactive, the button becomes the trigger for the whole capture flow. Electrically, one side of the button connects to a GPIO pin, and the other connects to ground or 3.3 volts, depending on your wiring. A pull-up or pull-down setting keeps the input from floating, so Python reads a clear pressed or not pressed state. The program watches for that state, starts the countdown, captures the image, and saves it. Debouncing is important because one physical press can create several rapid electrical transitions. A sensor-triggered booth feels less manual and more responsive. A PR sensor is useful when you only need to know that someone moved into the booth area. An ultrasonic sensor is better when distance matters, for example, when the person is within 50 centimeters. In both cases, the code compares the sensor reading to a threshold before taking the photo. That prevents random captures and gives the booth a clear decision rule. Detect presence, confirm the condition, then capture the image. Next, combine the pieces into one repeating program. First, the code initializes the camera and configures the GPIO pins for the trigger and any feedback devices, like an LED or buzzer. Then it waits quietly for a button press or sensor signal. When the trigger arrives, the program runs a short countdown, so users can pose and get ready. After the countdown, it captures the photo and saves it with a timestamped file name, preventing older photos from being overwritten. Finally, the program returns to waiting, ready for the next person. Test the booth the way an engineer would. Change one thing at a time, then try again. If photos are not saving, confirm the camera is connected, the save folder exists, permissions are allowed, and the code shows no errors. If the trigger fails, check power, wiring, and the exact GPIO pin number in your program. For better photos, adjust lighting, camera angle, background, and focus. Once it works reliably, add personality with a countdown LED, buzzer sound, preview screen, or props. You've now built a Raspberry Pi camera system that captures real-world images and organizes them into useful data. Buttons and sensors can trigger photos automatically, while timestamps and folders keep everything ready for analysis. Next, we'll move from capturing images to understanding them with AI concepts, detection systems, and an AI vision rover.